Number 1. The table below shows the temperature of a pot of soup that was removed from the stove at time t equals 0. What's the initial temperature of the soup? Well, the initial temperature is when I took it out of the stove at 100 degrees Celsius. What does the room temperature appear to be? So we see as time goes on, the soup begins to cool. And it looks like it's cooling to about 20 degrees Celsius would be my guess. 20 degrees Celsius would be my guess because we see it starts to taper off towards 20. And 60 minutes later, 1 hour later, it's pretty close to 20 degrees Celsius. So, find the decay constant K by using the temperature at time equals 10 minutes. So this is clearly a Newton's law of cooling problem. Do you need to memorize this? No, please don't waste your time with that. It will be given to you. So we know that T of T equals the ambient temperature plus the difference between the initial temperature and the ambient temperature times e to the negative kt, where k is this decay constant. Hopefully you flip back a page and copied Newton's law of cooling down from page 44 in your book. Well, the ambient temperature is 20 degrees. The temperature of the object, the soup, is 100 degrees minus 20, e to the negative kt. So the function we're working with here is 20 plus 80 e to the negative kt. And at 10 minutes, the soup is approximately, if I can slide up, 34.183. 34.183 degrees Celsius. So this lets me set up the equation. 34.183 equals 20 plus 80 e to the negative k, I don't know what k is, times 10. Well, I'm going to subtract 20 over and get 14.183 equals 80 e to the negative 10k. Divide by 80. That's some lovely number. So we get 14.183 over 80 equals e to the negative 10k. My variable's trapped in the exponent, so I have to natural log both sides to bring it down. Do I have to natural log? No, but because the number e is involved in this, I'm going to want to use the natural log. That brings my exponent and drags it down front. So I have the natural log of 14.183 over 80 equals negative 10k ln e. But guess what? The natural log of e is 1. Then I divide by negative 10 to get my decay constant k. So let me go to my calculator and type this in. The natural log of 14.183 over 80 divided by 80. Close the logarithm. Divided by negative 10. So my decay constant is 0.17. I'm going to assume we're going to round that up to 3. Yeah, let's go to 3 places of k equals negative, back to my calculator, not negative, 0.173. 0.173. That's our decay constant. So back up here into our Newton's law of cooling, we can plug that in, and I believe that's the next part. Write a function for the temperature of the soup as a function of time in minutes. So, using Newton's law of cooling, the temperature is 20 plus 80 e to the negative k, negative 0.173 t. That's on the previous slide for me, but all I did was I went to that Newton's law of cooling that we set up and plugged in our k value. Find the temperature of the soup after 40 minutes by using your function. So we want to find T of 40. So we're going to plug in a 40 for T and type that into our calculator. So on your calculator, we're going to type in 20 plus 80 e to the negative 0.173 times 40. And we get 20.079. So we get 20.079. Does this match your table? So we did 40 minutes. If I go back to 40, it does match. We did it correctly. At a diner, coffee initially had a temperature of 180 degrees Fahrenheit after being brewed. The coffee was poured in a cup and left in the diner, which had a temperature of 68 degrees. 4 minutes later, the coffee temperature was 140 degrees Fahrenheit. Clearly, this is Newton's law of cooling, and hopefully you flip back to the page where it was and rewrote it. T of T equals the ambient temperature, the temperature of the surroundings, plus the difference between the object and the surroundings, e to the negative kt. Well, what's the temperature of the surroundings? 68 plus, well, it started at 180 degrees minus 68 degrees, e to the negative kt. And if you do 180 minus 68, you end up with the function 68 plus 112 e to the negative kt. 4 minutes later, the coffee was 140 degrees. 4 minutes later, it was 140 degrees. So let's plug that in. 4 minutes later, it equaled 140 degrees. And now we solve this equation. Now we solve this equation for K to get our decay constant, and we're going to have to end up using logs because it's trapped in the exponent. So we subtract over that 68, and we get 72 equals 112 e to the negative 4k. Divide by 112. Maybe that's a nice number, maybe not. It's not a nice number, so leave it as a fraction. So 72 over 112 equals e to the negative 4k. Well, I'm going to natural log both sides to bring that down. So I get the natural log of 72 over 112 equals negative 4k ln. But the natural log of e is 1. So to get k by itself, I divide by negative 4. So in my calculator, that's what I'm going to type in. The natural log of 72 over 112, the natural log of 72 divided by 112, divided by negative 4. Yes. Hit enter. So our decay constant is 0.11. 0.11 is a good approximation there. So the decay constant is 0.11. So K equals 0.11. So going back to our function over here, the function is 68 plus 112 e to the negative 0.11 t. Find the temperature after 10 minutes. Well, guess what I'm going to do with 10 minutes? Plug that in for t. So t of 10 is 68 plus 112, and by 112 I mean 112, e to the negative 0.11 times 10. Type that into your calculator. 68 plus 112 e to the negative 0.11 times 10. So the temperature of the coffee was about 105.3 degrees. About 105.3 degrees Fahrenheit. That's the temperature of the coffee. What is the temperature after a few hours have elapsed? This is a key thing where it's talking about the hours that have elapsed. Our function's in terms of minutes. After 10 minutes, we're already down to 105.3 degrees. After a couple hours, it's going to approach, so after a few hours, it's going to start approaching 68 degrees. It's going to start approaching 68 degrees Fahrenheit because that's the room of the temperature. That's the temperature of the room, not the room of the temperature of the room. What is the percent rate of change of the difference between the temperature of the room and the temperature of the coffee? So we need to use our property of exponents to manipulate this expression here. I want to manipulate that expression. I add e to the negative 0.11. This is going to reveal the rate of change. So if I go to my calculator and do e to the negative 0.11, that's the base of my exponential function. Clearly it's decay because it's smaller than 1. I do 1 minus that number and times 100 to make it a percent. So it's decaying by about 10.5% per minute. So the difference between the temperature of the room and the coffee is decaying, we're getting smaller, decreasing by 10.5% per minute. Every minute, the temperature loses about 10% of its 10% of its degrees Fahrenheit. It goes down by about 10% every minute.